We all have at least seen one audio visualizer by now, be it the NCS circle in the Strad which told us live lessons, or some waveform generated by a program like Audacity. But have you ever wondered how it worked? I myself have, at least whilst making this project. I do know some of the basics of how audio works, both in terms of real life and in terms of how it is stored and processed in data. But what fascinates me is the idea of turning that stream of numbers into a coherent, visually pleasing spectacle. The first thing will of course be to somehow play the audio without making new forms of radio corruption. Because I will once again be using STL, this is rather simple, as STL includes audio functionality. For that I just need to initialize it the same way I can initialize video. Then I want to be able to drag and drop audio files into the program window to play. It turns out it is rather quite simple. Similar to the STL event fit, there is also a STL event drop file, where the file path is stored in event drop data. From there I can use SND file to quickly test whether it is a normal audio file. If it is, I then just simply use STL to make an audio stream which plays the file. Next, before I then get to visualizing the audio, I still need a bit of more functionality for this crude MPV replacement. To add some basic functionality like rewinding, I just need to implement the STL event key down, which when triggered I use to check whether it is a space, which I use to pause and resume the audio stream, or left or right, in which case I use SF seed with -5 or 5 respectively, multiplied by the sample rate, and clear the audio stream so STL also updates what it is playing. Now all that remained was a audio progress bar and a quick fix so that I can replace the audio file without needing to restart the program. Now that that is done, I think it is finally time to actually do some audio visualization. The way that I'm going to be calling on the audio is that my audio_callback function copies the currently played amplitudes into a buffer, which will store them for the visualizer to access. What this buffer precisely stores is a large list of differences in amplitudes. These are floats which vary between 1 and -1. And for my first test, I just used these values on a horizontal line to display points vertically. In the process I discovered that I can skip over a second value as it is the one for the other channel, and seeing as most channels being commonly the same, there seems little reason to be processing them both. I also exclude all samples with a value of 0 as they are boring. Now to finish my first very crude visualizer, what I did was I used FABSF to get the absolute number of the amplitude of each sample, displaced all the points to the bottom of the visualizer and turned them into lines, starting at the bottom, reaching to the amplitude. Whilst this is not the greatest of all visualizers, it is a nice place to start from, and even despite its simplicity, there is already visible correlations between its output and the sound it is playing. Naturally, I also made another version of the same thing, with the difference that instead of for each sample drawing a line from the bottom of the area towards the top, tapping the length based on the amplitude, what I do for this one is that all of my lines start at the center of the area and move away in the shape of a circle. What I've also done for this one is I have added a slight bit of rendered amplitude to all samples so the circle has a minimum radius. Whilst it looks nicer this way, I think it is still missing something so that the higher amplitudes don't seem so extreme. Now I could apply a simple formula like subtracting an arbitrary number from all samples higher than 0.5, however without even testing it out I already know this will not look good. What could instead work is if I for all samples above 0.5 subtract 10% of everything above the 0.5 bar from it. Now whilst I don't see a clear improvement, something I have observed by just looking at a couple of freeze frames of the visualization is that a bigger issue seems to be that even in just one frame the sample can differ by quite a lot from each other. To solve this, what I will implement is that every sample except the first, which instead checks for the last, checks for the previous sample and interpolates slightly closer to it. Now after implementing what I think was supposed to be that, I think either my computer is mad at me, or I need to go back to first class of maths and ternary statements. Okay, turns out it wasn't either of those, but just an embarrassingly simple mistake. And I think for once this actually was something which has improved the output. Now I'm sure there are more ways to improve the smoothing of the circle, and I am of course excited to hear the suggestions from all of you. However, before that I will just quickly implement so that the visualizer background is filled with the thumbnail of the audio file that is being played instead of just a blue box. My next idea is that instead of rendering every single amplitude being played during one frame, I use averages. The plan is that I have a number for how many bars I want, and the program then divides the list of amplitudes into that groups, of which it takes the average as the value for the bar. This does work, however it is not very interesting. I think the primary reason is that the samples are not distributed in any form of order, meaning that taking an average just leads to very similar values. Something that should at least slightly help with that is to not take the average, but just instead take the relevant samples as the value for the bar. And you know what? It does look very similar to most visualizers one sees nowadays. The last idea on how to improve this that comes to my mind for now is to sort the samples in order of values before getting averages and then scrambling the order in which the bars get rendered. Although after implementing this it does look less appealing than I would have hoped. Unfortunately, the individual bars don't really change that much in relation to each other, which makes them look less interesting. I could probably fix this by introducing an offset which gets changed every couple of seconds, but alas, I have no interest in that. Originally this was where I wanted to end the video, but that is not a satisfying conclusion. And after all, I think I can still do better. Let's consider what would be an optimal outcome. One where the bars change a lot based on the current sound. But what we actually perceive most is in fact not the volume itself, but rather the change in intensity. So it means that we likely perceive in music the change more than the absolute volume. So the conclusion to draw from this is that we should be visualizing the change instead of the absolute volume. Now let's think. What actually changes when the audio changes? Well, of course, the amplitude. And that is the one thing we have not yet visualized with these bars yet. For my final idea today, what I'm going to do is I'm going to plot the changes in amplitudes frame over frame on vertical bars. In theory, this should result in drops causing a spike which normalizes when the amplitudes remain constant. To do this, I simply need to create a second list of amplitudes, which we assign the current amplitudes to at the end of the frame before processing it in the next frame. The sample value which then gets rendered is now simply derived by subtracting the old sample from the current sample. The last thing I will do to make this look better is use every nth sample for a bar instead of rendering 500 of them. And finally, we got a result which I find rather amicable. But this brings up the question, how would this look if we were to incorporate the pitch and the overall amplitude? With this much data we could visualize it three-dimensionally. Maybe the pitch affects the other axis whilst the overall amplitude determines the color. I've got a lot of ideas on how I can improve this, and I'm sure some of you also have more great ideas on how to improve this visualizer. So please do tell me in the comments your ideas, and if you want to see them added to this, or just tell me that calculating the x-axis starting point every frame is inefficient. I would love to hear it. Until then, if you want to mess around with the code yourself, then the repository to that is in the description. If you have enjoyed listening to me ramble unnecessarily in depth about code, then I'm sure you will also enjoy this video about making your crude software rasterizer. On the other hand, if you want to learn how to code yourself, then the other video on screen about the universal basics of programming will be the perfect place to start. And all that now remains for me to say is thank you for watching.